In this course, we're mostly concerned with linear systems. And so let's look at the fundamentals of linearity. First of all, how do we define linearity? So if we have some function y equals f of x, so y is the output of this function and f of x defines how the function behaves. And x is usually going to be a signal here. So we can say that f as the function is going to map values of x to values of y. So if we let x equal some alpha x1 plus beta x2, and we let y1 equal to f of x1 and y2 equals to f of x2. So we haven't done anything magical here. For any value x, we can choose alpha and beta and other values of x such that those values make up x. That is, for any value x1 and x2, we can choose alpha and beta so that we get x on the left-hand side. And likewise, if we choose those values of x1 from the previous equation and x2 from the second equation, we should get values of y1 and y2 if we just substitute them back into the original equation. So with these sort of made-up equations here, now that we've defined them, function f is linear if and only if f of alpha x1 plus beta x2, that is, we take the original value of f of x and decompose it into alpha x1 plus beta x2, is equal to alpha times y1 plus beta times y2. So we've basically shown that we can, if you want to think of it this way, move alpha out of the function and beta out of the function, and we'll get the same answer. So this is how we define linearity. Let's look at a couple of examples. So here's a simple line at the origin. Y is equal to 3x. So the question is y linear as a function? So 3 times x is the same as 3 times alpha x1 plus beta x2. And we can just do a little parenthetical multiplication here. Alpha 3x1 plus beta 3x2. Now we remember we choose those values of x1 and x2 to come up with function values y1 and y2. But we can see 3x1 corresponds to y1, 3x2 corresponds to y2, therefore we have alpha y1 plus beta y2. Therefore, our system is linear here. Here's an example of a line with a non-zero y-intercept. Y equals mx plus b. You guys probably remember this from kindergarten or whenever it was that you studied lines and slope intercepts and all that kind of good stuff. So we do the same formulation. X is alpha x1 plus beta x2. And y1 equals substituting in values for x1 and x2. So now we need to check, are these two systems equivalent? So we substitute in on the left-hand side m times x, substituting in that new value for x plus b, and we do a little bit of rewriting to come up with this. Now we similarly on the right-hand side say we want y to be alpha y1 plus beta y2, so that's alpha times mx1 plus b, we got that from this value y1 right up here, and beta y2. So with this value, the question is, are these two pieces equivalent? Nope, not so much. The problem is b on the left-hand side is not multiplied by the alpha plus beta. So here we can see that this system of a line, y equals mx plus b, you've been told your whole life that this is linear. Well, it's not a linear system. It's not a linear equation that gives us the property of linearity. So here's another example. How do we show for a multivariate function that that function is linear? So let's say we have y equals 5x minus 2u plus d. So in this particular system, we're assuming that x, u, and d are individual variables and not constants. So x is going to be alpha x1, u is alpha u1, d is alpha d1, etc. So in this case, we want to substitute these values back into the equation and check for linearity. Likewise, y1 and y2 are going to be these values on the right-hand side, where we go ahead and substitute in x, u, and d as the variables. So now, with a little bit of writing on the left, we substitute in x, u, and d, and we can separate out alpha x1, alpha u1, alpha d1, and now we have all of our alphas in the left-hand group of variables and all of our betas in the right-hand group. After we separate those out, we can actually see that y1 is here and y2 is there. So that gives us the property of linearity for this system. What about a sinusoidal function? You can probably already guess, but let's show why this system is not linear. So let's say we have sine omega t, and here we consider that omega is in the real numbers. So omega is not a variable, only t is the variable. And by the way, we don't always have to use x when we show linearity. We can substitute t as any other variable as we like. So y1 is sine of omega t1, y2 is sine of omega t2, and now we rewrite t as alpha t1 plus beta t2, and we substitute that in for the function f of t. So now we see that above omega times quantity alpha t1 plus beta t2, we can multiply in the omegas, but now we have one of those complicated trigonometric identities. Sine of a plus b is sine a cosine b plus sine b cosine a. And once we plug that out, we get that value. We can likewise, for y1 and y2, multiply by alpha and beta to get alpha sine omega t1, beta sine omega t2. So we have to show that alpha y1 plus beta y2 is equal to f of alpha t1 plus beta t2. And in fact, you can see that they're not. However, well, so we can do a little bit more work here. So we can see that as we write these things out, there's really no way to get rid of that problem. We're always going to have this issue that whenever you want to pull variables from the inside of a sine function, it just never works. And again, you've probably already known this since you were in high school. However, we can consider some values of omega and some values of t. In this case, if we choose that omega is really, really small and that t is much, much less than infinity, then we can actually rewrite sine of alpha omega t1 as alpha omega t1. That is, the sine of a small angle is actually the small angle. And the cosine of a small angle is approximately 1. So we do the same for the beta values. And now we can rewrite the left-hand side as alpha omega t1 plus beta omega t2. On the right-hand side, we do a similar equivalence for sine of omega t1 and omega t2. And we actually get alpha omega t1 plus beta omega t2. So this is interesting. If omega is really small, and for t really close to the origin, this is an appropriately linear system. That is, it's not going to be perfectly linear, but we can make an approximation using the small angle approximation to get a linear system out of it. But it's only valid for small times, that is, when t is sufficiently small. If you make t really, really big, then it doesn't matter how small omega is, you're going to get a value for sine of omega t that's out of its linear range. So sometimes when you're designing a system, if you know that you have a fast reaction time, for example, you'll be able to say, oh, well, even though the system isn't actually linear, I can approximate it as a linear system for a little bit. And if I can keep it in the linear range, then I won't have to worry about the system going nonlinear on me. We'll see this as we do system linearization later, because that's going to allow us to show that we can keep the system within its linear operating range using feedback control. And if we can keep it in its linear operating range, well, first of all, we have to know what range is that system valid for. And that's why we do extra analysis on systems like this.